get started on changes to the reactant. Hopefully you know from what we've done before that there are some reactions that don't go to completion, and for these reactions they will start out with a certain amount of product, a reactant, sorry, and I'm drawing that very well. Freehand, hopefully you'll be kind that what we would say is that equilibrium has been established at that point there because we can't see any changes in concentrations of our reactants and products. And we also refer to this as dynamic equilibrium because what is actually happening is that the rate of the forward reaction is equal to the rate of the reverse reaction. It's not that everything's stopped. What it's saying is that if we're producing some product still, but we're also going back in the reverse direction and producing some reactants at the same rate. So even though we sort of focus on this equilibrium and say, okay, the reaction has stopped, we're talking about on a macro scale. We're not talking about on a micro scale. And so we're assuming that we've done our reaction, and we've reached equilibrium like I've represented here. Now what we're going to do is then take this reaction that has reached equilibrium and do something to it. We might change the temperature, we might change the pressure, we might change the concentration of a reactant or a product, and then we will see a relatively rapid change in response to what we've done to this reaction, and then we'll reach a new equilibrium. So that's what we're going to be doing with Lecitatelier's principle. So Henri Lecitalier is a French chemist, and he developed Lecitatelier's principle, where the system is going to adjust to partially counteract the change. Okay, so if you look in the top of the box on the middle of page 23, this is Lecitatelier's principle. The system at equilibrium is subjected to an imposed change. Then the position of the equilibrium will adjust so as to partially counteract the imposed change. It can't ever go back to where it was before, but it will come back closer to where it was before. So the system adjusts to partially, or to minimize the change, if you like. We only need to write LCP to represent Lecitatelier's principle. So the system adjusts to partially decrease the change. It's important for us to know whether our reaction is exothermic or endothermic for an increase or a decrease in temperature. Because if we think about reactants plus products, what would we say that kind of reaction is? Endothermic. Now, if I think about this in terms of Lecitatelier's principle, if I increase the temperature, so just say I did this reaction first time at 40 degrees, and then I do it at 50 degrees, what that means is I've increased the heat, haven't I? So if the system adjusts to partially decrease the heat, it's going to favour the forward reaction for an endothermic reaction and I'll produce more products. Is that sort of making sense? Just say I had an exothermic reaction. Okay, so just to remind you, this is exothermic. And again, this one might be done at 40 degrees. Well, let's make it 80 degrees. Doesn't matter. What happens if I increase it to 100 degrees? Now I've got more heat. And I should really, I guess, be using reversible reaction arrows here. But now I've increased the heat on this side. And Lecitate's principle tells me that the change will be made to minimise this change. And so I'm going to have more reactants. Okay, I'm going to push the equilibrium in the reverse direction to minimise the change. I can't ever go back to where I was before, but I can try and, the system will try and minimise that, the change that was made. All right, so if we read through the box on the bottom of page 23 here, if I increase the concentration or the partial pressure of a substance, right, so Lecitate's principle tells us that the change that will occur will be to minimise that concentration. So if we look at example 1 on page 24, we've got this equilibrium reaction. Between nitrogen dioxide and dinitrogen tetroxide. And we're told that the forward reaction is exothermic. Now, if we have our change, if we want to increase the temperature, this is the format, the best format that you should use to answer these changes to equilibrium questions is using this format of CER. Okay, so you write down what the change is. You write down the effect, and you must always refer to Lecitate's principle in the effect, because this is your justification, the scientific knowledge that you're using to say what's going to happen, and then there we have the result. So here we have this reaction, and we're going to assume that we're starting at equilibrium. So it doesn't matter which one's on top, the reactants or the products, but we have straight lines to represent it. And in fact, I've got them around the other way, so I'll do it the same as in soluble. Okay, so here we are, we're at equilibrium. That's all those straight lines are representing, and we don't know how much we have. Doesn't matter. All we want to be able to indicate is what's going to happen to the system if I change the temperature. Well, we're increasing the temperature. Okay, so that our change was the increase in the temperature. So the effect is the system will adjust to decrease temperature. Lecitate's principle. And the result, we're going to say which direction is favoured. I already told you over here that for an exothermic reaction, we're going to favour the reverse reaction. So that will mean our concentration of the nitrogen dioxide will increase. And it increases fastest at the beginning. Okay, so we have to think about our curve there. And then it will continue on once it's reached its new equilibrium. But when we're looking at our relative sizes of the change, we need to consider the ratio from the equation. So this is going to be 2x, isn't it? Where it's going to increase by 2x, but we're going to decrease our concentration of our nitrogen tetroxide by x. Okay, and then the 2 here, this is just because of the 2 here, and x because we've only got 1 there. So the result will be the reverse reaction is favored. We're going to increase the concentration of the nitrogen dioxide. Do we change K? Does the equilibrium constant itself change? Yes, it does, because we change the temperature. Remember, K is a constant at a particular temperature. And so if we change the temperature, we're going to change the value for K. Would K increase or decrease? Because remember, K is going to be the concentration of our products divided by our
decrease?
Yeah. So in this case, K will decrease. Equilibrium moves to the left. Alright, so part B, describe what will happen when the pressure is increased. So we've still got this reaction here. Now, if I change to increase the pressure, so the effect is the system will adjust to partially decrease pressure. Remember, Lecitate's principle must be included, you'll lose half a mark at least if you don't write LCP. And then the result. Okay, so let's have our graph again. And so NO2, N2O4. I'm going to increase the pressure. If the system is going to adjust to partially decrease the pressure, this is where we look at the mole ratio, or the mole on either side of the reaction arrows. Because here, in this case, I've only got one reactant and one product, but I've got a mole ratio of 2 to 1 for the whole reaction. So if I'm thinking about gases, and basically they're going to be behaving like an ideal gas, then this one's going to occupy less space, isn't it? So if I increase the pressure, the forward reaction is going to be favoured because there's less moles of gas. So we have our forward reaction favoured. We can justify it 2:1 mole ratio. And so the equilibrium moves to the right. K is unchanged. And because we're also told up here that this was brown and this is colourless, then the reaction mixture is going to be lighter. It will be a lighter brown. Okay, so now if we're looking at our equilibrium values meant to be horizontal, we generally, this is where we still need to use those rulers that we have. Continue it on with a dashed line so that you can see what you're working against. And our N2O4 here is going to increase. But we increase the pressure of the whole vessel, so the most common way of doing that would be to decrease the volume. So our change is going to involve an increase in concentration for them both. And even though it's not clear in your booklets, because we have a 2:1 ratio here and we were at equilibrium, and if we think, well, just say we halved the volume of the container, then we're going to still have more NO2. Okay, our concentration is going to be bigger than our N2O4. Okay, so both of them went up initially, and then our forward reaction is favoured, and so our concentration of the N2O, really, sorry, I should have that off there. Same with these ones, I should have done that first, sorry. This one is going to increase, and again it increases by X rather than just X because there's no coefficient there. And this one is going to decrease by 2X. Relative to where it would have been after we increased the pressure. We can't go back. Sometimes I see sort of sloppy diagrams, you know, where this one sort of just comes back like that. That's incorrect, and it cannot be correct because we cannot ever have a lower concentration than we had before. Does that make sense? That our 2X here is going to be less than our original equilibrium. So we just need to take a little bit of care in drawing these diagrams. Alright, we've got another example on page 25. How about you set yourself up some axes and have a go, and we'll see what... well, actually, just set yourself up some axes and I'll work through it with you. I know we've got axes in here, but it's better if you write it out yourself. Okay, we have this famous reaction, the Haber process. As I said, extended World War I by just 18 months, killed millions of people. basically. All right. So we're asked to predict the effect on the position of the equilibrium for the following imposed changes. So we would always just start out by putting our reactants, giving each of them a line, and then we'll see what's going to happen. So for part one, we add some nitrogen gas. CER, so the change is an increase in the pressure, partial pressure, of the nitrogen. The effect will be that the system adjusts to partially decrease pressure, LCP. Alright, so now if we look at, that part's pretty easy, don't you think? Like, we just need to recognise the change and then say that the system's going to try and minimise it. Now what's going to happen to our graph? Well, we've increased our nitrogen, and the system is going to adjust to partially decrease the nitrogen. So we must be favouring the forward reaction, mustn't we? So the forward reaction is favoured. Equilibrium moves to the right, and K is constant. And there's no change to K because we didn't change the temperature. So when we're looking at what does our graph look like? Well, we only increase the partial pressure of the nitrogen. So it has a bit that goes up from its original equilibrium position, but the other two remain the same. So now I can draw my dashed line across from there and say that, well, we're going to end up using up that nitrogen we added in. And if I look at the balanced reaction, there's only a 1 in front of the N, so this will then be minus X. If we look to see what's going to happen to our hydrogen, it's going to also get used up as well, isn't it? Because it's a reactant, but because of the 3 in front of the hydrogen, this is going to be minus 3x. And we're going to be producing more ammonia, and our coefficient tells us that would be then plus 2x. When you're doing this, and you can see that mine's a little bit on the dodgy side, but you want to make sure that your minus x is roughly worth a unit, and that this is worth that 2 of those units, and this is worth 3 of those units. Just approximately. You don't need to be getting out the ruler and measuring the millimetres, but you want to make sure that they make sense in the context of the question relative to each other. And but they don't, this really should be, like, they should be straight lines. So once you've reached equilibrium, wherever it is that you're deciding your equilibrium has been reached, you should use a ruler to make that a flat straight line. Okay, so that was change number 1. Number 2, we're removing some hydrogen gas. So the change would be to decrease the partial pressure of the hydrogen gas. The effect could be the system adjusts to partially increase the hydrogen pressure. Okay, so let's have a look and see what's going to happen this time. Going to be removing some hydrogen gas, and so my initial change is to reduce the concentration of the hydrogen gas that's present for our reaction. Now, if the system is going to adjust to partially increase the hydrogen, we must be going to favour the reverse reaction, mustn't we, to put that hydrogen back. So the equilibrium moves to the left, reverse reaction favoured, no change to chapter K. So what's this going to look like? We can just have our dashed lines again, coming off from where they are after the change has been made to the system. And we're going to try and put hydrogen back, aren't we? So this is again where we have to make sure when we put the hydrogen back, we don't go back to having more than we had before. Our X values here are still related to our balance equation. So that's going to go up. Our ammonia is going to go down. By 2x, and our nitrogen will also go up by x. Now, in this one, in our next example, number 3, an increase in the total pressure at constant pressure. So we're going to increase the pressure of the whole system. Change is an increase in pressure. The effect is that the system adjusts to partially decrease pressure. And let's have a look at the result. Now again, this is one where we need to look at our mole ratio. So we've got 4 moles of reactants and 2 moles of products. And so if the system is going to adjust to partially decrease the pressure, we will favour the forward reaction where we have less moles. So the forward reaction is favoured. So equilibrium right. K is changed. Okay, is it making sense that what we're doing is we're just looking to see what happens each time we change something? Now, we increase the pressure of the vessel, the whole vessel, and so we're going to see that they all increase in concentration at the same time, when, like, if we think that we basically just press the vessel. And now we're favouring the forward reaction. Remember that we need to consider our equilibrium relative to our new concentrations. So we're favouring the forward reaction. We're going to produce more of our ammonia. Plus 2x. We're going to be using up our 3x. And I'm going to actually make this one smaller because I have to make sure that I don't drop down lower than my original concentration there.
Can you return to the original?
And then this will go up by x.
I believe you can. That's what I should be adjusted, completely adjust.
Okay.
Now, if we increase the temperature, we did talk about this one before.
So doesn't nitrogen decrease?
Oh, sorry, yes, it does. Yes, because we're using that as a. So another result we could say is that we increase the production of the ammonia and those sorts of things, parts I'm not sort of going over, but that might be relevant depending on the context of the question. Okay, so we talked about before what would happen with exothermic and endothermic changes. So if we're going to change the temperature now, increase in temperature. So we know that if for an exothermic reaction, that means heat product. And so if I increase the temperature, the system is going to adjust to decrease the temperature. So it will favour the reverse reaction. So the result will be that the reverse reaction is favoured, equilibrium moves to the left because this is an exothermic reaction. And K, what happens to K?
Increases?
So K is the concentration of what? What's on top? Products. So if I increase the reactants, K decreases, doesn't it? Alright, so we've increased the temperature and so we've made no adjustments to concentrations. All of our dashed lines come straight across from where they were originally. And we're going to be increasing our nitrogen, increasing our hydrogen, and decreasing our ammonia. That's like making sense? Okay. All right. Now, the addition of a catalyst. A catalyst increases the rate of reaction. It increases the rate of the forward and reverse reactions. And so, what's going to happen with a catalyst? Nothing changes. So let's look at catalyst. So we introduced a catalyst. We don't actually change the equilibrium when we add a catalyst. So, the position. I should say that's the position. But we do get there faster. So, how you might represent that would be like that. That we've actually reached our equilibrium faster. And so it just means that the curve here is steeper, and you're going to reach equilibrium sooner than you weren't using a catalyst. And our last one that we have there is removal of some of the ammonia gas. Well, I think you can see the pattern that's happening now. If I remove some of that ammonia, the system is going to adjust to replace the ammonia, won't it? So we're going to favour the forward reaction. Equilibrium moves right. K is unchanged. So back on our diagram over here, we would see a step down here because we've removed some ammonia. The other two stay the same. Now we're going to be increasing our ammonia from our new position here, and we're going to need to decrease our concentrations of our reactants. Okay, so hopefully that's enough of a guide there through those examples for you to have a bit of a go. There's another example, but I'll stop now so that you can start working on the questions on page 29. You can do another example next lesson if you like.